In the last video we talked about electric current and how this may flow through good conductors or resistors. Resistors make it harder for charges to flow and hence reduce the rate of flow of charge, i.e. the electric current. But how do we work out how much opposition to charge flow a resistor will present? We define a property called resistance, which is a function of three parameters. It is directly proportional to the resistivity ρ, which is a parameter related to the type of material that the resistor is made of. It also increases with the length of the resistor, since the longer it is, the more obstacles the charges will encounter. On the other hand, it is inversely proportional to the cross-sectional area of the resistor. This is because the larger this area is, the more gaps there will be between obstacles for the charges to sneak through. It stands to reason that the amount of current that will flow through a resistor when we connect a battery across its terminals will be proportional to the voltage applied across it. The more potential energy the charges have, the faster they will be able to flow, and the more charge will go through a specific volume in a given time. It also stands to reason that, considering that the function of a resistor is that of slowing down the flow of charge, the current will be inversely proportional to the resistance, which tells us how much opposition to charge flow there will be in a specific resistor. There is a very simple linear equation which applies to many cases, which allows us to express these intuitive physical facts in a mathematical form, and this is called Ohm's Law. It tells us that the current through a resistor is equal to the voltage across its terminals divided by the value of the resistance itself. So suppose that we have two resistors connected in series, that is to say, one right after the other. We can again use a battery which will give us a constant voltage across its terminals, and then we connect this series of resistors across the terminals of the battery. The charges will start flowing and they will flow through the first resistor and lose some potential energy as they do so. And then they flow through the second one and lose more potential energy. The battery maintains a constant voltage between its terminals, and so we have a constant flow of charges through the circuit. Because we have this constant flow of charges, if we measure the voltage at point A, which tells us how much potential energy the charges have at the very stage after they've gone through the resistor R1, this will also be constant, because we will have the same amount of charge flowing through the resistor at any one time, and that amount of charge after it's gone through the resistor R1 will have lost the same amount of potential energy. Another important point to make is that when we have two resistors connected in series, the electric current through both of them will be the same. This stems from the principle of conservation of charge, which you will be taught in another unit called Fields and Devices, and this states that the charge is neither created or destroyed and thus remains constant in a closed system. Based on this principle, all the charge that flows through R1 must also flow through R2. Let's try and make this a little bit more intuitive by resorting to a water analogy. Suppose that we have a pump in a loop of water. So the water will begin to flow at a certain rate, and this rate will be determined by the natural resistance of the water. Note that in this case the white arrows indicate the intensity of the flow. So the fatter the arrow, the higher the flow rate of the water. Now, what happens if we now place a sand filter in this water loop? This is an obstacle to the water flow, and hence it will resist the pump which is attempting to push water through the pipe. The resistance provided by the sand filter to the circling water depends on the properties of the sand, of course, and will decrease the flow rate, and this is indicated by smaller arrows here. If we replace the sand filter in the previous slide with a sand filter which has got coarser sand, it will offer less resistance to the water flow because there will be larger gaps between the grains of sand. Now, what happens if we insert two sand filters in the loop identical to one another? The resistance to water flow that the two filters present does not depend on their separation, and hence there will be a single flow rate determined by the combination of those two filters. So we could replace these two sand filters with one single sand filter with the same type of sand, but twice the length. Similarly, we could replace those two sand filters with one single sand filter of the same length, but with sand which is twice as fine as the sand that we had in the two separate filters. So similarly to the sand filter examples, the current flowing through two resistors in series is the same and is determined by the combination of both their resistances. So just as in the water loop there was one flow rate, there is one rate of flow of charge for any loop in a circuit as well. So in order to calculate this flow rate, which is determined by the combination of R1 and R2, we could replace the two resistors with one single resistor Rs, which is equal to R1 plus R2. Then Ohm's law could be applied. And this will allow us to calculate the current I as the ratio of delta V, the voltage applied across the resistor series, divided by the sum of the two resistances. In general, if a circuit comprises of a single loop, the electric current through all elements in that loop will be the same.